In this lesson, we're going to learn to solve optimization problems. In optimization problems, we are looking for the largest value or the smallest value that a function can take within an interval. This interval is a set of restrictions to our solutions, which is known the domain of the function. In order to solve it, there are a few steps that we can follow. First, draw a diagram if necessary. Second, determine the function, which is a formula that represents the quantity to be optimized. Usually, you look at the last sentence to see what you are trying to optimize, which means maximize or minimize. Step 3, you want to make sure there's only one variable in the domain. That means you want to manipulate the equations so that there's only one variable in the domain. And step 4, you find the domain of the function to be optimized, and now we can differentiate. After you differentiate it, you let your first differentiation equal to 0 to find the critical points. And then you have to determine and identify the maximum and minimum of each critical point. And then you have to check with your endpoint to see the absolute maximum and minimum in order for you to have a conclusion. Example number 1, there is a piece of metal 60 centimeters by 30 centimeters that is to be used to make a rectangular box with an open top. Find the dimensions that will give the box with the largest volume. Step 1, we need to do a diagram. So first, we draw a rectangle and label this 60 centimeters by 30 centimeters. Second, because we need to make an open top box, that means we have to cut out the 4 corners in order to fold them to become a box. So the 4 corners that we have to cut out must be squares. And third, let's label the side length of the 4 corners to be x. Because we use the variable x on the diagram, so we have to define what x is. So we have to write a let statement. Let x represents the length of the sides of the squares at the corner in centimeter. Step 2, we need to determine a function that represents the quantity to be optimized. In this question, the quantity that we need to optimize is the volume because the question says largest volume. So even though we are finding the dimension, but the quantity needs to be optimized is actually the volume. So let's write an equation of the volume of the box. V equals length times by the width times by the height. As you can see here, there are 3 variables in the domain. But in order to do optimization, we only have 1 variable in the domain. So now let's move on to step 3, manipulating the equation so that we only have 1 variable in the domain. Let's look at our diagram again. Originally, our length is 60 centimeters, but since we have to make a box, we have to cut out the corners. That means I cut out x centimeters here, x centimeters here. So now the new length will become 60 minus 2x. Same thing again. The width originally is 30 centimeters, but I have to cut out the x here, I have to cut out the x here. So now the new width will be 30 minus 2x. And because the side length of the square is actually x, and when we fold it, the x actually becomes the height of the box. So the height is x. So now we can replace the 3 different variables in the domain into 1 single variable. After we have the equation and we have 1 variable in the domain, now we have to move on to step 4, find our domain. Domain is a set of the conditions that we have to follow. So in this question here, we have 3 different conditions. So first is the length. Length can never be smaller than 0 or greater than 60. The width can never be greater than 30 and smaller than 0. The height must be greater than 0. Now let's write it down. 0 less than L less than 60. And we know length is 60 minus 2x. Subtract 60 on all the intervals and divide by -2 to isolate for x. But when you divide by -2, the inequality sign switch. Likewise, let's do for the width. Subtract 30 on all the intervals and divided by -2, once again, the inequality sign switch. And we know the height must be greater than 0. That means x must be greater than 0. Since we have to satisfy all the conditions, therefore we can say our domain will be 0 less than x less than 15. After we find our domain, then we are ready to do step 5, differentiation. Since this function can be easily expanded, so we're going to expand it and use power rule to differentiate. After we have the expanded form, then we can differentiate. And remember to common factor them. Once we have our differentiation, then we can do step 6. Let v prime to be 0 to find and identify our critical point. Because this quadratic function, it's not factorable, so then we have to use the quadratic formula to find our critical points. Once we use the quadratic formula, we will find out it's 15 plus 5 root 3, which is approximately 23.66, which is outside our domain. So this critical point is invalid. And the other one is 15 minus 5 root 3, which is approximately 6.34, which is within our domain. So this is our critical point. Now let's identify the critical point. Let's put the v prime on, put the critical point on, and remember the boundaries between 0 and 15, and that's tested out the positive and negative sign. On the left-hand side, the critical point is positive. On the right-hand side, it's a negative. So this means function is increasing and decreasing, so we have a local maximum. At 15 minus 5 root 3, and there's a volume. Step 7, we need to make sure that this is the absolute maximum, so we have to check with our endpoints. But as you can see here, the endpoints for 0 and 15, there is no equal sign on. That means the endpoints are not being included, so it's not applicable. Therefore, this is our answer. 15 minus 5 root 3 will be the x value to have the maximum volume. Last step, we have to find our conclusions. Because the question only wants us to find the dimension, they didn't ask us to find the volume. So I just need to find the length and the width and the height by substituting the x values that we find into the length and the width and the height. After you find the length and the width and the height, remember to make a final conclusion. So you will say, therefore, the dimension of the box is length times by the width times by the height. The length and the width can interchange, but the height must be the last one. Let's look at example number 2. Andrew and John are both training for a marathon. Andrew's house is located 20 kilometers north of John's house. At 9 o'clock one Saturday morning, Andrew leaves his house and jogs south at 8 kilometers per hour. At the same time, John leaves his house and jogs east at 6 kilometers per hour. When are Andrew and John closest together, given that they both run for 2.5 hours? First, let's do a diagram. At 9 o'clock, Andrew and John are 20 kilometers apart. As the time goes on, Andrew will go south and John will go east. And we know distance equals speed times by time. So Andrew is leaving at 8 kilometers per hour. That means 8 times by t. And t represents the time after 9 o'clock. And John will go east. Same thing again. Distance equals speed times by time. And John is going at 6 kilometers per hour. So this distance will be 6t. And at 11:30, Andrew will reach John's location and John will be on the east side of Andrew. Next step, we have to find the equation. Even though we are looking for time, because when are Andrew and John closest together, but we are minimizing the distance between them. So our equation has to be in terms of the distance. So if you look at this diagram in the middle right here, so the distance between Andrew and John can be modeled by Pythagorean theorem. We know the Pythagorean theorem is a squared plus b squared equals to c squared. So let's look at a. the whole thing here is 20 kilometers, and this is the distance that Andrew has already traveled, which is AT. So the remaining distance will be 20 minus AT. And this one is 6T, and this one is our distance. Therefore, we have D squared equals to 20 minus AT squared plus 6T squared. And let's look at our domain. Domain is a set of restrictions that have on this question. So because our variable in the domain is t, so we have to look at the restriction for t. So look at the time, it's from 9 o'clock to 11:30. So I know the duration of the time will be from 0 hours to 2.5 hours. So this is our domain. Once you have the equation and the domain, then we are ready to differentiate. But once again, this will be easier to differentiate if we have the expanded form. So we expand it and remove the square by taking the square root. And we use chain rule to differentiate it. So bring down exponent take away 1 times by differentiation of the base. And we let d prime to be 0 to find out the critical points. And we can put the negative exponent into the denominator. As you can see, denominator will never become a 0. Therefore, our critical points will be on our numerator. So let the numerator equals to 0. So 200t minus 320 will be 0. Then we find t equals 1.6. Then we have to identify our critical point by drawing a number line for d prime and put the critical point on, which is 1.6, and put the endpoints on, which is 0 and 2.5, and check the positive negative sign. So as you can see, this is negative, that's positive. That means the original equation is decreasing and then increasing. This will result a local minimum at t equals 1.6. And we have to check with our endpoint, which is at 0 and 2.5. So how do I find all those d values? Then we have to substitute the t value, which is 1.6 and 0 and 2.5, into the original equation to find out our value for d. And you will see that's a 12 and 20 and 15. And that's compare all those values to see which is the smallest one. And you can see 12 is the smallest number of all three of them. So this will become a global minimum, which is the absolute minimum, and that will become our answer. So now let's go back to the question to see what do we need to find. The question is asking for when. So look at our time. That's 1.6 hours after 9 o'clock. So if we want to find the time, we have to change the 1.6 hours into 1 hour and 36 minutes. How do I get the 36 minutes? You do 0.6 times by 60 to get 36 minutes. And then that means that's 1 hour and 36 minutes after 9 o'clock. So it will be at 10:36 a.m. They are closest together. Example number 3. A cylindrical chemical storage tank with a capacity of 1,000 meter cube is to be constructed in a warehouse. And there is a dimension of the warehouse that is 12 meters by 15 meters and the height of 11 meters. And they tell us the cost of each side of the cylinder. So it says the base of the cylinder will be $100 per meter square, and the top will be $50 per meter square, and the side, which is the wall, will be $80 per meter square. And our goal is to find the dimension that will minimize the cost of the construction. First, let's draw a diagram. The green one represents the warehouse, which is 12 by 15 by 11. And the purple one is the cylindrical tank that we are going to build inside the warehouse. Let's label the radius and let's label the height. Next, we're going to find the equation that we are trying to optimize. Here is we are minimizing the cost of the construction. That means our equation will be in terms of the cost of the cylinder. So let's look at a cylinder. On the top, it's a circle. So area is pi r square times by the price, which is 100, plus the cost of the bottom, which is also a circle, which is pi r square, times by the price, which is 50. And let's look at the side wall of the cylinder. The area will be 2 pi r h and times by the price, which is $80. As you can see, now we have two variables in the domain, which is not allowed. So that's replace either the R in terms of the H or H in terms of the R. Look at the question here. It says the volume of the cylinder must be 1,000 meter cube. So we know 1,000 equals pi r square h. But since there are a lot of r square here, so it will be easier to isolate for h. That means replace the h in terms of the r. So that's divided by pi r square here. So we will have h equals to 1,000 over pi r square. And that's replace the h and simplify the equation to have one variable in the domain, r. Once you only have one variable in the domain, then we can find the restrictions. So let's look at the diagram again. The maximum radius can have will be half of a 12 or half of 15. So we know it has to be half of 12 because it cannot be more than that. So the maximum radius will be 6. Now, the minimum radius, if there is no warehouse, will be 0. However, since there is a warehouse, that means the maximum height we can only have is 11. So we're going to try to find if the height is already at the maximum, what will be the minimum radius we can have. So substitute 11 into the volume equation, we will find the radius must be 5.38 because we need to have a volume of 1,000 meter cube. So we know the lower bound for the radius will be 5.38. Once you have the equation and the domain, then you are ready to differentiate. And after you find the first differentiation, that equal to 0 to find the critical points. After you find the critical points, make sure that this value is within the range of the domain and put it on the number line, put the endpoints down to check the positive and negative sign. This is negative, this is positive means decreasing, increasing. This will result in a local minimum at radius 5.54. And we have to check with our endpoints because there's no equal sign on the inequality sign of the domain. That means the endpoints are not being included. Therefore, R equals 5.54 will be our answer. And then let's go back to the question to see what we need to find. The question here is finding the dimension that will minimize the cost. So we have to find our height of the cylinder. So we put the radius 5.54 into the volume equation. The volume is 1,000, pi is 3.14, radius is 5.54, and then you can isolate for h and solve for h. And you will see the height will be approximately 10.38 meters. Therefore, we say the minimum cost occurs when the radius is approximately 5.54 meters and the height is approximately 10.38 meters. Example number 4. A commuter train carries 2,000 passengers daily and the cost to ride the train is $7 per person. Market research shows that 40 fewer people will ride the train for each 10 cents increase in the fare. And there is a limitation of the capacity. The maximum people they can carry is 2,600 passengers, and the minimum in order for them to operate the train will be 1,600 passengers. So the question here is, what's the price we should charge the passenger in order to get the maximum revenue? Here, a diagram is not necessary, but we do need to find the equation of the revenue because that's the quantity that we need to optimize. So we know the revenue equals the number of passengers times by the price per ticket. So let's put the original information in. We have 2,000 passengers and each person will be $7 per person. And let's put the research in. It says every single 10 cents increase will result in 40 fewer people. So I can add another $0.1, then you can lose another 40 passengers, and I can add another $0.1 and you lose another 40 passengers. That really means I can put the X beside 0.1 represents the amount of times I increase the price by 10 cents. Then that will be the same amount of times that you're going to lose 40 passengers. Once you have a generated equation with only one variable in the domain, that means we are ready to find the restriction of the domain. So we know there's a capacity limitations for number of passengers, has to be between 1,600 to 2,600. So first, let's replace number of passengers with a mathematical expression, 2,000 minus 40x. And then we're going to isolate for x, that means we'll subtract 2,000 from each interval. So you're going to have negative 400, small equals to negative 40x, smaller or equals to 600. And since we have to isolate for x, that means I have to divide it by negative 40. Whenever you divide it by a negative number, the inequality sign will switch. So it becomes 10 greater or equals to x, greater or equals to negative 15. And this is our domain. Now we have the equation and we have the domain. We're ready to differentiate. And once again, we expand it to make it easier to differentiate. And after that, we'll let the first differentiation equal to 0 to find the critical points, and we find x is negative 10. And we put it on the number line for r prime to identify whether or not that's a maximum or minimum, and just make sure that you put the domain on negative 15 and 10. And on the left hand side, you see it's a positive, means increasing. On the right hand side, it's negative, means decreasing. So there is a local maximum. And after we have the local maximum at x equals negative 10, that's checked with the endpoints, which is x equals negative 15 and x equals to 10. Substitute those x values into the revenue equation to find out the revenue. And that's how we came up with those three revenue different values. And you will see which is the highest number. You will see 14400 is the maximum revenue. So this becomes our absolute maximum. That will be our answer. Therefore, let's make a conclusion. We want to find the price per ticket. So we know the price per ticket is 7 plus 0.1x. And we know x will be negative 10. So we put negative 10 into the x, we get the price is $6. And final statement, therefore, the fare should be $6 per person in order to get the maximum possible revenue. Example number 5 is talking about how to build the power line from a power station to an island to minimize the cost. So the first information we have is the island is 4 kilometers away from the shore. Whenever they talk about 4 kilometers away from the shore, that will be the shortest possible distance. That means it's perpendicular to the shore. So this is a 90 degrees angle right there. And there's a power station down the shoreline, which is 8 kilometers. So from the power station, we're going to build certain distance under the ground and go across the water to reach the island. After we have the diagram, then we are going to generate the equation for the cost, which is what we are trying to minimize. The cost will be the price for power under the ground plus the cost for the power line that is built under the water. So the price for the cable under the ground will be $300 times by the distance underground. So we are going to say X is the amount of distance that doesn't have the power line. So that means the amount of power line under the ground will be A minus X. And then the amount of power line that is under the water can be found by using the Pythagorean theorem. So a squared plus b squared equals to c squared. That means x squared plus 16 equals to the distance for the power line under the water. That means the distance for under the water will be square root of 16 plus x squared. After we have the equation, then we're going to find the domain. So look at the possible values for x. So the minimum will be 0, and that means the maximum x value will be at 8. And then after we have the equation and the domain, we are ready to differentiate. After you differentiate it, let c prime to be 0 to find the critical points. And usually when I see a negative exponent, I will move them into the denominator and square both sides to get rid of the square root. And you will find x squared equals to 2. And after that, we take the square root, but you have to including a positive sign and negative sign. The negative square root 2 will be invalid. That means you're just building on the other side. So we don't worry about the other side because our domain is between 0 and 8. And that's put in on the number line. For positive square root 2, make sure you put the domains on 0 and 8. Check the positive and negative interval. So this size negative means decreasing. This size positive means increasing. That means we are going to have a local minimum. And once again, we have to check with our points, endpoints, which is at x equal to 0 and x equals to 8. Substitute those three x values into the original cost equation, not C prime, the C function, to find out the price we have to pay. And look at which is the lowest C value. We'll see $5,794 is the lowest one, so it becomes our absolute minimum. This is our solution. Therefore, we will say we build a minus root 2 kilometers under the ground. That will minimize the cost. Example number 6, we are finding the minimum distance from the curve y equals the square root of x to the point 1.5 and 0. As you can see from the graph, the distance from the curve to the point is really the distance between the 2 points. The first point will be 1.5 and 0. The second point is any point along this curve, x and y. So for this question, the equation that we're going to use will be the distance between 2 points. So our x1 will be 1.5, our y1 will be 0, our x2 will be x, and y2 will be just y, any point along the curve. But we know y equals the square root of x, so we're going to replace the y with the square root of x. And after that, just expand and simplify, you will have a function. Next, we have to find our domain. The domain is all the possible x values that we can use. Since the x is inside the square root, so we know x has to be greater or equal to 0. So our domain is x is greater or equal to 0. After we have the function, we have the domain, we can differentiate, use the chain rule. And after that, you let d prime to be 0 to find the critical points, and you will see x is at 1. And we have to identify what kind of critical point we have at x equals to 1. So put it on the number line for d prime, put the 1 on, put the endpoints on. Right now, we only have one end, x equal to 0. Left-hand side will be negative, which is decreasing. Right-hand side is positive, means increasing. So this will result in a local minimum at x equals to 1. And that's checked with our endpoint, x equal to 0. Substitute those two x values into the original distance function to find out the distance. We will see root 5 over 2 for x equals to 1 and 3 over 2 for x equals to 0. Because root 5 over 2 is smaller than 3 over 2, so we say this is our absolute minimum. Therefore, we will say the minimum distance is root 5 over 2 at x equals to 1. Example number 7, we want to find the dimension of the largest right cylinder. That means we are trying to find the maximum volume that can be inscribed in the cone with a radius of 3 meters and height of 6 meters. First, let's draw a cone and then draw a cylinder that is inside the cone, and we're going to label them. So we know the height of the cone is 6 meters, and we know the radius of the cone is 3 meters. However, we do not know the dimension of the cylinder. So let's label radius as r, and because I say this part is the h, so the height of the cylinder becomes 6 minus h. Because the question wants us to find the largest right cylinder, that means we are trying to maximize the volume. So our equation is the volume of a cylinder, which is area at the base, which is a circle, times by the height of the cylinder, 6 minus h. And then we see there are two variables in the domain, which is not allowed. That means we have to replace r into h or h into r. So let's look at our diagram again. We can see there are two similar triangles, and we're using the similar triangle properties. We know h over r, it will be 6 over 3. So that's write the equation down. H over R equals to 6 over 3. And we know 6 over 3 is 2 times by R on both sides. We get H equals to 2R. So now let's replace the H with a 2R. Now we have a new equation with a one variable in the domain. Before we differentiate, now we have to find the restriction of the domain. So let's look at the diagram. This is the radius. We know the minimum radius will be almost at 0, but not 0 because volume will be 0. And then the maximum will be almost at 3. So our domain is between 0 and 3 now. Now that's differentiated. Once you differentiate it, remember to common factor them, so it will be easier to find the critical points. Let the v prime to be 0 to find the critical points. You will see r equal to 0 or r equals to 2. But because of the domain, we know r has to be greater than 0, so this critical point will be invalid. Let's put it on the number line for v prime and put the critical point on 2 and put the endpoints on 0 and 3, and let's check the positive and negative interval. On the left hand side is positive means increasing, right hand side is negative means decreasing, so we are going to have a local maximum at r equals to 2. After we have the local maximum, we have to check with our endpoints. Because there's no equal sign on the inequality for the domain, that means the endpoints are not being included, therefore not applicable. Therefore, we know the maximum volume will happen when radius equals to 2. And then we need to find the height because the question is asking for dimension, and we don't need to find the volume because the question didn't ask for it. So the height of the cylinder will be 6 minus h. And we know h equals to 2 times by the radius, which is 2 times by 2, which is 4. So 6 minus 4, it's 2. So we know the dimension with the maximum volume will occur when the radius is 2 meters and the height is 2 meters. Example number 8. There is a rectangular piece of land is to be fenced in using two kinds of fencing. And two opposite sides will be fenced using standard fencing that costs $6 per meter, while the other two sides will require heavy-duty fencing that costs $9 per meter. What are dimensions of the rectangular lot of the greatest area that can be fenced in for a cost of $9,000? First, let's draw a rectangle, label length and width. Second, let's find our equation. Even though we are finding the dimensions of the rectangle, but we are maximizing the area. So your equation has to be in terms of the area. So area of the rectangle is length times by the width. However, I see there are two variables in the domain. That means I have to replace one of them. So I go back to the question to look for more information. I see that we have $9,000 and we have to pay for two kinds of different fencing. So I said that L represents the length of the rectangle that requires heavy-duty fencing. So now I know the amount of price I have to pay for this side will be 9 times by L. And this side will be 6 times by W. Then I can create an equation just for the total cost of the fencing and collect the like terms and simplify it. I see W is 750 minus 3 over 2L. And that's substitute the W into the equation. So now we can generate a new equation with only one variable, L, in the domain. Before we differentiate, we have to find the domain, the restriction for L. So let's look at this equation here. 3L plus 2W equals to 1,500. So the lower bound for L, that means the minimum length that you can have for the rectangle is almost 0. But what will be the maximum? The maximum is when the W is almost 0. So then if W is almost 0, that means 3L is almost at 1,500. That means L is almost at 500. So I know the lower bound will be 0, the upper bound will be 500. Now we have the equation and domain. Then we are ready to differentiate. After you differentiate it, let your first differentiation equal to 0 to find the critical points. You will see L is 250, which is within our domain. And then you check the positive and negative interval by putting it on the number line for L prime, and you will see that will be a local maximum. And Let's check with the endpoints. Because there's no equal sign on the inequality, that means the endpoints are not applicable. And let's go back to the questions. We are finding the dimensions. We are not finding the maximum area. So all we need to do now is to find out the width by using this equation here. So the width is 750 minus 3 over 2 times by L. Substituting 250 for L, you will see the width is 375 meters. Finally, let's make a conclusion. So we say the greatest area occurs when 250 meters require heavy-duty fencing and 375 meters requires standard fencing. Example number 9, we are finding two positive numbers with a product equal to 200 such that the sum of one number and twice the other number is as small as possible. So what will be the minimum value of the sum? This question doesn't require a diagram. So the first thing is to find the equation. Since we are finding the minimum sum, so our equation is in terms of the sum. The sum of a number x plus twice the other number 2y. Now, because there are two variables in the domain, that means I have to replace one of the variables. So let's go back to the question. We know the product has to be 200. So I know x times by y has to be 200. That means I can isolate y to be 200 over x. That's substitute the y into the y here. So I got 2 times by 200 over x. Then I got a new equation with only one variable in the domain, x. Next, we have to find our restriction for the x because they say x is a positive number, so we know the domain is x greater than 0. Once we have the equation, we have the domain, now we can differentiate. Once you differentiate it, you let it equal to 0 to find the critical points. You get 0 equals 1 over 400 over x squared. I move the negative 400 over x squared to the left-hand side, so it becomes a positive. And then I multiply by x squared on both sides, and I get x squared equals to 400. Now, removing the square by taking the square root, you have to have a positive negative sign, but we know x can never be negative, so the negative 20 is invalid. Next thing we have to do is identify the critical point at x equals to 20. Put it on the number line for s prime, and put the critical point on 20, put the endpoints on 0, and check the positive negative sign. You will see left-hand side is negative, decreasing, right-hand side is positive, increasing. That means we're going to have a local minimum. Once again, because there's no equal sign on the domain for the inequality sign, so we know the endpoints are not being included. Therefore, we know the x value is 20. Finally, we have to find the minimum value of the sum. So let's go back to the equation here. Sum equals x plus 2 times by 200 over x. We know x is 20, so we put 20 plus 2 times by 200 over 20, which is 20 plus 20. That will be 40. So we say the minimum value of the sum is 40. Example number 10, a closed box with a square base is to contain 252 centimeter cube. The bottom cost 5 cents per centimeter square, the top cost 2 cents per centimeter square, and the side cost 3 cents per centimeter square. I want to find the dimension, which means the side length of the base and the height that will minimize the cost to construct this box. Since we are minimizing the cost, so our equations in terms of the cost of constructing the box. So the cost will be the area times by the price. The first one is the top one, will be a square, x squared times by the price, 5 cents. So which is 0.05 times by x squared. The bottom one is also a square, which is x squared times by the price, 0.02. Now we have 4 equal sides. And each side, the area of each side will be x times by h. So we know x times by h is each rectangle, and we have 4 of them, and each one will be $0.03. And add them all up, that will be the cost for constructing the box. After that, you will see there are two variables in the domain. So once again, that's not allowed. So let's look at the questions to see whether or not there's any more information. We see the volume has to be 252 centimeter cube. And we know the volume of the box will be length times by the width times by the height. So that's put in on the side. Length times by the width, which is x times by the height, h is 252. So we can isolate h to be 252 over x squared. And that substitute in, simplified it, now you will have a new equation with only one variable in the domain, x. Before we differentiate, we have to find the domain. Since x represents the side length of the square base, so the only restriction on x will be greater than 0. So our domain, x greater than 0. Now we have an equation and the domain, then we are ready to do differentiation. After you find the differentiation, let your first differentiation equal to 0 to find the critical points. You will see x is going to be at 6. And then that's put in on the number line for c prime. And we know on the left-hand side of 6 is negative, on the right-hand side is positive. That means decreasing, increasing. That will result a local minimum at x equals to 6. Now, let's check with the endpoints because there's no equal sign on the inequality in the domain. Therefore, the endpoints are not being included. Therefore, not applicable. Therefore, we know the minimum cost will occur when you have x equals to 6. Now, let's go back to the question to see what we need to find. It says we need to find the dimension, but it didn't say we need to find the cost. So all we need to find now is to find h. So we know h is 252 divided by x squared. Substituting 6 into x, you get h equals to 7. Therefore, the side length is 6 centimeters and the height of the box is 7 centimeters. Question 11. If two smokestacks are located 20 kilometers apart and one is emitting 7 times as much smoke as the other, where on the road between the two stacks should the building be built so that the concentration of the smoke is minimum? First, let's draw a diagram. And second, I said that K represents the amount of smoke from the smaller stack. Then this bigger smokestack, when emitting 7 times more, will be 7K. And I say the distance between the little house and the smaller stack is x kilometers. That means the distance from the house to the bigger one will be 20 minus x. Next, let's find our equation. Since we are finding the minimum concentration of the smoke, so my equation will be concentration. And how do I find the equation now? Let's read the question. It says a concentration that is inversely proportional to the square of the distance from the foot of the stack. So the amount of smoke that this house is getting from the smaller stack will be the concentration of the smoke, K. Inversely proportional means over the distance square, x squared, plus the amount of smoke that this house is getting from the bigger, smaller stack. So the concentration of the smoke is 7K. So we have a 7K on the numerator. Inverse proportional means over the distance, which is 20 minus x, whole thing squared. So now we generate the equation. After we have the equation, we have to determine the restriction of the domain. So let's look at our diagram. The minimum x value will be almost 0. That's the distance between the house and the small stack. So we couldn't say that's 0 because you cannot build the house on top of the small stack. Same thing again, the maximum x value will be almost at 20. So our domain will be 0 less than x less than 20. Now we have an equation, we have the domain, we are ready to do differentiation. Once you differentiate it, let the first differentiation equal to 0 to find the critical points. You will see x is approximately 6.87, which is within our boundary of the domain. And then you put it on the C prime to check the positive negative sign. So on the left-hand side of the critical point is negative, means original function is decreasing. On the right-hand side is positive, means increasing. So this will result a local minimum. So we know the minimum concentration will occur when the distance x will be 6.87 kilometers. Now we have to check with our endpoints because there's no equal sign on the inequality. That means the endpoints are not being included. so not applicable. Therefore, we will say the building should be built around 6.87 kilometers away from the smaller smokestack.